Hi everyone, we're going to start in just a second. Hello, it's good to be back with Imagine webinars. So good morning, Guillaume.
Good morning, Patrick.
So as everyone can notice, we're wearing our masks. So just briefly to show you
our
face.
I remove my mask when I talk.
And so we're back today. Sorry for the fact that we had to reschedule this webinar from late September to late October, but COVID and other constraints have created a number of inconveniences in our work and probably in yours too. So I'm Patrick Sheen. I'm the Chief Digital Officer at Imagine Optic.
And I'm Guillaume Dovillaire. I'm a Chief Technical Officer here at Imagine Optic.
And this morning, we're going to talk about a lot of new, very exciting things. And Guillaume will give us some details before performing a live demo. At the end of the session, we'll have a Q&A session. And you'll be able to ask whichever questions you want all along the webinar using the Q&A function. In the little panel you have in probably the right corner of your screen, where you can find chat and other useful functions. We're very happy to be back, as I said before, and I'm going to stop the presentation. So here we go, and hopefully it's going to work. Yes, so this is this morning agenda. We're going to talk about a bunch of new products and new functionalities, as I mentioned before. But to summarize it in one phrase, Guillaume, what is the main theme of the webinar this morning?
This morning we present a complete new generation of Wavefront Sensing tools. We'll talk about both hardware and software. The technology has a lot evolved this last decade, so Wavefront Sensing inherits of this evolution in cameras and electronic parts, software things. We'll focus today on the HASO4 BroadBand, which is a new generation of Wavefront sensors, and we'll focus also on software. You'll see today the new Waveview4 software, and I think we will present today a small revolution in terms of Wavefront sensing, because we add the feature SpotTracker in our sensors, which allows a lot of things with our Wavefront sensors. It's a small revolution. You'll see this. I'll explain what this feature is. It will greatly improve and simplify the life of scientists and optics engineers.
Well, thank you, Guillaume. So before we dive in this very rich program, just a quick word about Imagine Optic. We're a company specializing in optical metrology and specifically wavefront sensors, but we also have skills and products in adaptive optics. And what's maybe our main characteristic is we've been around for over 20 years, and we were among the pioneers of shock-Hartman technologies. But we keep innovating, and that's what really this morning webinar is about. And we'll hear more in detail about what you do. And so to start with our first innovation, the HASO4.
Yeah, so the name BroadBand means something, which means that this sensor is calibrated in the whole range, 350 nanometers to 1100. I remove my mask because I will talk a lot. Patrick, if you want
so I'll be in the distance. Bye-bye.
So, hi, everyone. Um, this sensor is smaller, is very robust, it's very easy to mount, it's insensitive to vibration. You can get rid of air turbulence by averaging measurements. And for the people who don't know us, we use the Shy-Kapman technology. And you have to keep in mind that Shy-Kapman technology is still the golden standard in wavefront sensing. As we measure wavefront and intensity maps simultaneously, it's possible to calculate bond spread function, modulation transfer function alive, and a small focus on the energies. This technology allows to measure wavefront with a very small amount of energy. We're talking about 8 picojoule of energy per image, which means that if you set exposure duration of the camera with, let's say, 10 milliseconds, can do the measurement with less than 1 nanowatt of flux. It's compatible with many accessories we have, and of course, maybe some of you already saw the webinar about our Flex 2 and large aperture systems. Of course, this sensor was compatible with these two products. We can now switch to, in order to present to what's the SpotTracker feature I talked about just before, I have to just remind you how works Shy-Kapman wavefront sensor. It's an association between a microlenses array, here drawing is in green, and a detector. It can be a CMOS camera or a CCD camera. If you imagine wavefront coming here, each microlens will create a spot on the detector. And if the wavefront is not flat anymore, the spot will be shifted compared to the microlens's axis. So at the end, the camera signal is a array of spots, and the algorithm have to calculate the position of each spot to finally retrieve the local slope of the wavefront, and then by to the integration, give the wavefront. Why we create this SpotTracker approach? Because Shy-Kapman sensors have basically a spot recognition problem. And I want to emphasize something here. It's not a problem of Shy-Kapman sensors, because many other techniques able to measure the wavefront create a pattern which is very regular, and other techniques of wavefront sensing have the same issue here. But for the Shy-Kapman technology, what happened is that if you imagine flat wavefront, it creates spots, as I said, in the axis of the microlens. If you tilt this wavefront, the spot will be shifted, and there is a tilt corresponding to the fact that this microlens here will create a spot which is on the axis of another microlens. And in both cases, the camera signal required by the camera is strictly identical. So if you're at the place of the software, you have this matrix of spots, it's impossible to say which spot corresponds to which microlens, which is a problem. And this is really a problem. Because if you can't recognize which spot corresponds to which microlens, there are too many consequences. The first one is that you measure badly the tilt, because the tilt, you can't measure it. And the second thing is that the calibration of the sensor, the reference, is subtracted in the shift. And it creates systematic errors in the wavefront. So what we did in this sensor is that we add SpotTracker technology. So it allows the user not to have to learn the sensor, because the idea we had before this technology is to insist on the fact that the sensor must be aligned compared to the beam in order to reduce the tilt, to be sure that the association between the spot and the microlens is correct. So the software will now detect automatically which spot must be associated with which microlens. If some of you already know our product, you have this trimmer button in our old release software. This is a magic hat. This is like an evolution of this function, but very, very more robust. And this technology is possible because it's an association of a very specific microlenses array design and, of course, a software feature. So you have now no doubt on the display tilt, no risk of subtracting calibration or reference to the shift, and it's not significant in terms of calculation frequency because at the end calculation is quite wide.
Well, that's very impressive, Guillaume. So if I try to summarize that, it's a bit like having an expert help you align the wavefront sensor with the optical alignment.
Yeah, it's like somebody who say, okay, put the sensor anywhere in the bench. Each have light, the sensor will measure the wavefront without any dot on its accuracy. So it's quite an expert with you when you use the sensor.
So I guess this is something we will see during the live demo later on.
Yeah.
But maybe just a word about Waveview4, because Waveview4 is also a big part of this new function, and there are tons of new functionalities in the new release of Waveview.
Yes, our software team did a great job this last year in order to propose to our customer this new software at a small resolution. In order to give you an idea, we had an idea with Patrick, just to remind you what was the very old version of our software, 1999, with our first wavefront sensors. We had the first software. It was written in C and LabVIEW. Basically, a wavefront sensor software is a hardware interface with a camera through a camera manufacturer SDK, and then it's image calculation in order to retrieve the flows, calculation to retrieve the wavefront, and then display all the possible diagnostics. So in 1999, we had this first release, and after we switched to HASO4, which was our first real software. In 2002, we had the dynamic projection, was compatible with many different cameras. And then the most common software we used since 2009 was HASO4, more dynamic, faster, but was still written in C++ in LabVIEW. We had 3D things here. And here in 2016, maybe some of you use Waveview. We create this name here. It was a release 3.1. And at this time, we create a complete new calculation code. So we call this tool code 4. It was written in LabVIEW. And now, please welcome to a complete new era of wavefront sensing software. This is a picture of what we'll see today. As you see, it's a completely modern interface. Still wavefront slopes, transcribe function, and particle to see the parameters. You'll see this in details in the demo just after this. Small thing about all this. There is, sorry, Patrick. I think
no worries.
about that.
That was my next question, actually.
Yeah. All this was written, as I said, completely in C++ and Qt. So we are now the possibility to offer to a customer a complete SDK in C, C++, and Python. Here are two examples of our example we provide with our SDK.
Well, thank you, Guillaume. That's a great overview. So I think we're gonna dive into the live demo. Sorry, you had.
I have this picture of the software team here. We can see 5 of this team. I have Nicolas, Pauline, and Jerome. These 5 guys here, we work a lot on this software, and they are very proud to propose to you to this software to our customers today.
Sure. So let's move on. Maybe switch to the live demo.
Yeah, maybe we can just zoom on the camera.
Yes.
Sure.
Demo. I'm gonna
just to present you the bench. As you see, the bench is very, very simple. I have here, maybe some of you know the product. It's a small laser diode, which we call this SMLS, single mode laser driver. It's a single mode fiber connected here on the bench to a small holder. And we have here the wavefront sensor, just set here on the bench. And I can put the sensor everywhere. A small focus on this sensor. So this is, as I said, the HASO4 BroadBand. Then you can see more than here. But as you see, it's a very small thing. That's the camera here. There is light inside. It's a USB 3 connection here. And our mechanical engineer created a quite small interface here with the magnet. So you have 3 balls here, you can just click here, and you're sure that the sensor is exactly the same as it was before. So I can put this here again, and we'll switch to the software now. I have another tool here because I will show you a very simple lens. I will put this lens close to here, but we made it and see what happens. So let's stop now here and here. So as you see, Waveview can launch this now, and the main interface is now open. As I did some tests for this webinar, this is software automatic connected to 4795 wavefront sensor. It's connected. If you want to use many wavefront sensors connected to the same PC, you can just select in the list which one you want to use. So it's very easy to select if you have many wavefront sensor connected on your PC. Oh, the light switch off. I hope you can see me still. This here, as you see, this part here is dedicated to diagnostics. You have the parameter tree here with all parameters. The left part here is dedicated to acquisition. At the top part here, file management, addition to task. And on the right here, you can see all the possibility of diagnostic I will use today. So let's start the measurement. Maybe first I can show you the camera signal. It is. So as I said, it's metric spot. I can zoom here. Here I can change. If some of you don't like this Imagine Optic display, you can switch to display very easily. And I can zoom here. It's very easy also to change the scale in order to see things with low light. For instance, here, as you see, I set the maximum here of the auto scaling at 200 levels, total number of the camera. So you can see here the spots that are created by all the micrometers, and probably you can see live the noise of the camera, which appears here as low level. So as I said, after you acquire images, you are able to calculate the slope. You can just display the slope this way by just saying it's a small vector. Matrix of small vectors. I can zoom to increase the vector length here, as you see. I can zoom here in order to see all the small vectors moving due to air turbulence and noise. But what is more interesting in the software is, of course, the wavefront sensors. Let's have it on the wavefront sensor here. Maybe just before you saw me, I put the sensor on the table without any alignment. As I said, the wavefront is at the output of the single mode fiber. So we expect to have perfect spectral wavefront at the output of this fiber. But the distance between the fibers sensor is about 50 or 60 centimeters. So the wavefront at the scale of the cupid size of the sensor is a pure sphere. Here, you can't see the pure sphere because, as you may see here, I just filter the tilt and curvature. If I just display the tilt and the curvature, here is the wavefront. And if some of you will be able to find in 3 dimensions, this wavefront is basically tilt. The small thing here is a small curvature. It's displayed here. But as you see here, the wavefront peak to valley is 90 micron due to tilt and curvature. If I want to see what is the aberration, which is hidden behind this big tilt and curvature, I just have to remove the component tilt y, here, x, y, and curvature. And the residual is now, as you see here, if I just click here, I can zoom on this information in order to include the slide. I hope you can see this value. It's 4 nanometers here. And just to show you the power of this SpotTracker technology, if I now switch off the light, put the sensor somewhere else in the beam, switch on the light, oh, here, for instance, I think, to activate the feature here. No, it's not here. I'm sorry for that. Where did it? It's here. Yeah, SpotTracker. I'm sorry, it was disconnected during test. Yeah, here is the spot. So when I click here, the SpotTracker switch on, and then it allows me just to change the position of the sensor and put it anywhere in the beam. And each time, the association between the spot and the macro lens is automatic. I can show you the power of this by displaying the parameter. There's the tilt. Maybe you can see this information. I can add this in the zoom. So for that, Wavefront element is 5 nanometers and it is. Now I tilt the sensor. 90, 80, you see? I add 200, maybe nearly 200 milliradian of tilt. And the wavefront is still 8-9 nanometers. The wavefront sensor is now able to follow the spots and not to mix between spot and macro. What is the corresponding aberration now? If I display tilt and focus, as you see here, if I zoom on the wavefront now displayed peak to bottom, I have more than 1.3 millimeters of optical 1.3 millimeters, and still, if I click the tilt and judge, wavefront value is less than 8-9 nanometers. And this is very important for your application because in some conditions, you want to rely on wavefront sensor able to measure a huge amount of aberration. And that's the case here. This sensor in this demo is able to measure more than 2,000 fringes of aberration. If we count fringes like interferometers does, with an accuracy of 8-9 nanometers. It's quite interesting. Maybe some of you, I don't know if you can see the video now, but the sensor is completely tilted now because 200 milliradian is, let's say, a degrees. And it's very easy to see that the wavefront sensor is tilted. So imagine I want to measure the beam here. I just put the sensor closer to the beam, to the output fiber. So maybe you can see now that the saturation here, the image is saturating because we have too many flux. So I can just reduce the power of the source here. You can see maybe it's 50–60%, and the wavefront is still 4–5 nanometers. I can again tilt the sensor, tilt the wavefront in order to the wavefront sensor to see what happens even with a very huge amount of tilt. And wavefront is still 4 nanometers. I can do even more if I put the sensor very close to the source. Oh,
It's probably like 5 centimeters.
Yeah, it's more, maybe 40 millimeters. Now, the system says, okay, I can't calculate. Why I can't calculate? Because now we have a huge saturation. So I can just reduce the flux by changing the current in the laser diode. And here, without any alignment, pinholes, thing, trimmer function, just put the sensor. The wavefront is still 5–6 nanometers. And maybe I can display here the intensity profile. So I have to change a bit the colors in order to display the intensity profile. So you have here in live intensity profile and phase. So you have in live the measurement of the electrical field. As you see, the intensity profile is not perfectly centered because I didn't do any alignment. But this aberration, the measurement of the aberration is still as expected. A pure sphere with a ratio between 5 and 4 nanometers. In this condition, if I display curvature and tilt, as you see, the tilt is not very important, but the curvature is now 152 micron, just a curvature. And if I filter it, I still have 3 nanometers of residue. And I can easily now, when I have this line speed, I can just move the sensor due to sound resolution view. When it's not doing that, I can just orientate and the tilt of the wavefront in order to change the measured tilt. I just rotate the sensor around the axis so I can easily center it. A small focus on the software here on the left part. You have a lot of parameters. If you are confused about these parameters, we created this. This is a favorites parameter zone. So you can very easily say, okay, I'm very interested by this parameter here on SpotTracker. Say this, you can add this to the favorite, and it appears here. That means that you have at the bottom of this part all the parameters, and at the top the parameters you want to change every time you.
So if I understand correctly, Guillaume, this means I can create my own custom configuration with the parameters I use more frequently or I'm most interested in, a bit like bookmarks on a browser.
Okay. That and save configuration. You have save and load feature. It automatically saves the position of Windows and the parameters you added in this area here. So you can retrieve exactly the layout you want on this.
So one example of such an application for such a feature would be like aligning lasers or something.
Yeah, and this is what I can show you now. I can just say, okay, I will put a sensor at about 20 centimeters from the source. Of course, here, as you see, the saturation gives you 5% because as I increase the distance between the source and the sensor, the light incoming on the sensor is lower, so I can just increase the power of the source in order to retrieve a signal. Again, I just didn't do any alignment. The sensor say, okay, perfect, no aberration. This is as I expected because I'm still on a pure spherical wavefront. And I showed you just before that I have a lens here. I can just put the lens in the beam. Let's just see on the camera, see where is the beam because I can see it here. Oh, yeah. Where is my window? It's here. Okay, where is the beam? I will just move this here. As you see now, the beam is smaller because it's quite. I added the lens. Let's have it on the wavefront. There is an error because, of course, now I still have saturation. But I add the lens of beam that is too high. Just have a look on the wavefront. This is wavefront. It's very light. We still have the intensity here. Here, so we have again light wavefront intensity. And what I can do, for instance, is just say, okay, let's open the parameter window, have a look on the radius of curvature of the wavefront, which is minus 1.7 meter. So I can just try to collimate the beam by changing the position of this lens. As you see here, curvature radius increases, and then I can try to just collimate the beam easily, like up, as you see, changes the sign. The radius of curvature and that is now close to infinity. We sometimes prefer to use the curvature, which is inverse of this figure. So it's maybe easy to reduce this to 0 instead of increasing this to infinity. Now my beam is collimated. As you see, the wavefront still seems to have some aberration because probably my lens is a bit tilted. In order to have a more precise diagnostic on this aberration, I can quickly switch to Zenki projection. I can do this way. And as you see, the system now automatically detects the largest one pupil here, without any, I didn't configure any mask, anything. Automatically, the largest pupil is found, and then I can now display the density coefficient, which I'll display this way. And as you see, clearly, a small comma is visible. It's very collaboration. It's a doublet, but doublet still have a bit of collaboration. So I can try just to align this lens in order to reduce the ratio, the comma. Or I can reduce this comma to 0. I am now sure that this lens is perfectly adjusted in terms of aberration. I have no more aberration after this. So my collimation of this lens is now perfect.
So an application of this type of configuration would be like alignment, again, of optical setups.
Yeah, it can be alignment. Now, I just align all lenses on the beam, but I can, of course, now say, okay, I have to align another lens, telescope thing. I just have to put the sensor on the table, add the lens, and put the sensor to the second lens, and just get the beam. You align the aberration in the lens. And, finally, obtain the best optical system you can your own lens.
If I try to summarize that, you're building a complicated optical setups with many lenses you want to align. Just go one lens after the other.
Yeah.
Then time you put back the sensor, and with the SpotTracker function, you don't have to care about aligning the wavefront sensor again and again and again and again. So it's a lot easier. It's a lot of time gained.
And it's very easy to align one after another. I have a small joke about that because when we designed this wavefront sensor, we tried to find a comparison with those two, and I think the best comparison we can do is this sensor is like the oscilloscope of the optics engineer. You know, electric engineers use oscilloscope to put their wires to find what is the signal here and here on the electrical board. This is the same with the sensor. You have the sensor on the table, you have something to align, you put the sensor where the beam is, and it gives you a diagnostic on what is the optics aberration here at this point.
So simple.
Yeah, very simple. And if you want more diagnostics, you can, for instance, here I display the point spread function. As you see here, point spread function is, as I remove all the aberration, it's now a very nice point spread function. We have also, of course, a modulating point spread function and many other diagnostics you may discover these next weeks, months when you have the sensor and software.
So this is something we'll go back at the end of the live demo with that the HASO4 BroadBand is the first wavefront sensor with SpotTracker, but this comes along with Waveview4. So maybe a couple of more words about some of the new features, and I say some because there are many of them, and we're going to be detailing them through blog posts and other webinars in the weeks and months to come.
Yeah, I just can show you something. If I stop here, the software, those are stop the acquisitions. Now the image is frozen. If I come back to here, now I'm interested to see what this file. I just double click on this data file, and it opens a new instance of Waveview. So you can compare. You can have an instance running connected to the hardware running the measurement, and just clicking here, you have a new measurement because you saved this measurement the day before. You want to compare what you have. It's very easy now to just reopen files and compare things, and you can open the number of instances you want. Of course, you need many screens, but okay, you can open a lot of instances in order to compare files. Maybe here I can just show you this measurement. It was done last week on a telescope, on a 1 meter telescope. So that is why there is a central obscuration here. And as I said, the Zernike projection just found automatically the best pupil here in order to calculate the metrics. the Zanicki coefficient here, you can see that this telescope was not perfectly aligned. You have here clearly astigmatism and coma on this telescope. And there is some people will go back this weekend in order to try to align this telescope using Wavefront sensor from our company and try to remove astigmatism and coma. So this can be an example. I can show you also the mask feature, which was completely redesigned by our software engineer Pauline. If you're not interested in some part of this this measurement, you can just switch it off. As you see, it automatically.
Yeah, like a mask obscuring part of the beam.
If you're not interested by the central part, you can just put this. If you want to create an ellipse, you can just remove this. So it's very easy to change. If you want to create a mask, to change the part you want to use in the Zanicki calculation.
So a software mask, and this
software mask.
This comes with a number of new features and a complete redesign of Waveview, which makes things a lot easier, along with the integration of SpotTracker in the Wavefront sensor itself. Well, that's great. And maybe, as you mentioned in the agenda, because we're progressing towards the end of the webinar, maybe a couple of words on the software development kit, the SDK.
Yeah. Just before doing that, I can just show you the quantified function here because I think it's quite. And I just have here the quantified function of this telescope. Small propagation parameters here. I can change the focus of this in order to see what happened through focus. So I have -1, +1. You can see how it changes the quantified function through focus. And you have this display so in 3D. So you can just extract from this software. Very beautiful thing in order to include this in your
report. Yeah.
You can print this, and print is in fact, okay, I saved this in PNG format or BMP. You can save the raw data. If you want to reload this file to use your own 3D display thing. So there are many possibilities to extract things from this software. Just to come back to the SDK, as I presented, we have 4 different languages proposed with our SDK: C, C++, LabVIEW, and Python. The SDK is delivered with many examples, so you can very easily use all these functions in your own application. I don't know if you want to just you design a machine which needs a wavefront measurement for doing something. I just buy from us a wavefront sensor as the OEM customer, and we deliver to you only the wave kit, which is our SDK, and you use the function in order to include all the function and the features you just saw in Waveview4 in your own software. You can drive all the cameras, motors, and things in order to automatize your measurement.
Well, that's a great value proposition. Thank you, Guillaume. Maybe it would be a good time for our attendees to start asking questions in the Q&A section. I don't see many for now, but feel free to add them as we go towards the end of this webinar. Any other features you would like to demonstrate in this?
Yeah. I don't know if you can see just behind me on the camera. We just put the R-Flex 2 with the LA system. There's a new thing we designed at the end of last year. It allows to measure filters, large diameter filters, and things like this. We presented this software, this system in our last webinar in July, I think June or July. So if you're interested in this, you can just have a look on YouTube or on our website.
On our YouTube channel, absolutely. It was the first webinar we did together, actually.
So this is, and of course, the Wavefront sensor you just saw is compatible with this. Maybe you can just see on the camera that you can quickly see, quickly put this.
You want me to? Yeah, let me get it for you. There we go. And I'm going to put it on the bench. Okay. There it is.
Thank you, Patrick. And it is thanks to this very nice mechanical interface here. The sensor can be set here. Just on the 3 balls here, and yes, that's it.
And it's aligned.
Yeah, it's aligned. And the sensor is now set on the RFX2, which is set on the LA100, and we have a 100mm primitive beam available here. So if you put a flat mirror here, the beam is direct and measured by the Wavefront sensor. So like a zygo, like a physical interferometer, you can just measure the large diameter optics in this part, except that you're not sensitive to vibration, you're not sensitive to air turbulence because you can just average. You don't have low fringes, and it's quite cheaper than a physical interferometer.
So it's easier to operate, it's cheaper to acquire, and it's insensitive to vibrations.
I think we have a question here from Gatolis. What about low repetition late laser beam? Did you try? Yes, of course, we tried that. In fact, you have at the red, at that.
Do you want me to get rid of the element?
You have at the bottom, at the rare part of the sensor, a connector, and you can just set up here a TTL signal. So in that configuration, if you just sensor, change the parameter here, where is it? Acquisition parameter, maybe it's here. I don't have this parameter up here. I don't know why. But of course, this sensor, you can just set up the camera in order to trigger it on an external trigger. And we have many customers, they synchronize the laser beam on the Wavefront sensor. So they use the external synchronization of the laser in order to trigger the sensor. And it works very well, even on a very, very low repetition rate. So if you just set up the sensor, start the acquisition, sensor will wait for just one trigger. And if the trigger is launched, of course, the Wavefront, the acquisition is done just a few, I think it's a question of nanoseconds after the trigger raised. No, the trigger rose. Yeah.
Sure. Any other questions from our attendees this morning? Maybe if we don't have any more questions, we're going to proceed to the summary. Okay, so let's proceed to the summary. And we're done with the live demo. Questions and answers. You still can ask questions.
What is the effective wavelength range for sensor? We have another question. The Wavefront sensor is calibrated in the range 350 nanometers to 1100. And what is important to have in mind is that in this range, the accuracy of lambda 100 is very essential. That means that we managed to do calibration which is completely achromatic. If you're interested in other wavelengths, we have some other products, for instance, for square, for UV, and even for extreme UV, and even for X-rays. So if you work at different wavelengths, we can offer specific Wavefront sensors for you. Something I didn't say, maybe it can be quite like a start for a conclusion. For the very beginning of this Waveview software, we will offer this software only with new manufactured HASO4 BroadBand, so the sensor we use today. And little by little will include new compatibility for our other Wavefront sensors. So just keep connected to see if your sensor will become compatible with this software in the next month.
Yeah, we'll be releasing information about which sensor is compatible with Waveview4, as you mentioned. Waveview4 is now part of our new released Wavefront sensor, starting with the HASO4 BroadBand. And you will find a complete spec sheet of the HASO4 BroadBand in the handouts of this webinar. So it's using the same little panel that I mentioned before. And about the HASO4 BroadBand, the two, apart from integrating SpotTracker and being delivered with the brand new Waveview4, the main two characteristics is the wavelength range, which
is 350 to 1100 meters, and so the quite very nice design here by Lionel, our mechanical engineer, and the quite smart interface here with the magnetic thing, allowing you to set the sensor very easily on your bench.
Or an on-off flex too. Absolutely. So Waveview4, we've had the glance of some of the new features. You've seen that the layout has been completely redesigned, but and it allows for custom configuration to be saved for quicker configuration when you're repeating measurements, for example, or when you want to make sure that you're not wasting time finding the parameters over and over again. Now, SpotTracker was definitely the star of this webinar. I think you got that. So very useful feature for alignments of lasers and metrology in general. You mentioned telescope alignments also, which is something we've done quite a lot. Well, you have done quite a lot in the past 10 years. And we concluded with the software development kit, the SDK, which is now available in 4 languages with tons of examples that you can build upon to create your own integration within your system.
Yeah, we can add something here where, as you see, I took a picture of the software team. If some of you have some problem using our SDK or our software, we have quite a very powerful support system here for our customers. We want to do the best support as possible, and this is in the strategy of this company. So do not hesitate to ask. We'll be very pleased to help you in using the SDK, using our product. It's important that you can use our software and product the best as possible.
Yes, so confidence is something we're definitely stressing upon, and the Waveview4 actually went under a full year of beta testing, so we're now confident that everything is in place, although some of the functions are still in unusual areas. For people like you who've been using Waveview 3.1 for many past years. But as Guillaume said, we're committed to providing support to our customers. So feel free to contact us. And if you don't mind, I'm going to ask you very quickly 3 questions just to be able to support you more currently in the next few weeks. So my first question to you is, would you like to receive a copy of the presentation we used this morning? So please take a minute to answer that. And I will have 2 other quick questions for you. So Couple of seconds left to answer this first question if you want to receive the presentation we used this morning. And thank you for answering this first question. We're now going to a second question is, are you actively looking for a solution these days on some of the topics that we covered this morning, which is alignment of optical systems, lasers, and more generally, applications that are connected to the use of HASO4 BroadBand and Waveview4. So I'll give you a couple more seconds to answer the second question. And thank you for answering. So we'll move to the last question is, would you like to receive more information on the topics we talked about this morning? Possibly Waveview4 or the HASO4 BroadBand? If you do like to receive more information, one member of our sales team will get in touch with you. And as I mentioned earlier in the handouts for this webinar, in the small panel, you can find an application note on Wavefront Sensing and absolute measurements and the specification sheet about our HASO4 BroadBand. You will also find information, and thank you for answering this last question. You will also find information on Waveview4 going to our website, which is at imagine-optic.com. Here's the homepage. And feel free to contact us if you have any further question. I think it's time now for us to say goodbye. So I'll join Guillaume.
Oh, I have to put my mouth.
Please do. So bye-bye, everyone. Thank you for joining. And we'll see you next month for another webinar on Square. So we'll demonstrate new products, which is a brand new HASO Square with an R-Flex and an air lake that are also dedicated to Square wavelengths. Thank you very much for watching.
Thank you very much. Thank you, guys.
Bye-bye.
See you soon.